Sounds on, yes. So that's what we call a pulley system. In past years, I guess this was maybe even part of the curriculum. You would do this. You would have a formula to calculate the leverage that one could have by doing the same amount of work, but having the output of work be much greater by having a series of pulleys, but it's not anymore. Let's just put that in there. And I'm just going to Google search atwood machines. So, I don't think I'm going to give you anything like that, so don't freak out. But when I search Atwood, that's what I get. So you think a pulley system was named after some dude named Atwood? Maybe. Okay, this is, and they can get quite a bit more complicated, but basically, if you want a picture of what we're doing today, that would be it right there. Okay, just two masses, one pulley, still forces, so it's still dynamics. Again, it's part 7. So, any guesses as to what's going to happen here? It's going to fall, yes. Which one? Probably the 8 kilogram one, yeah. That's common sense. That's not physics. And, well, let me just write this. Obviously, the 8 kilogram mass will go down, and if it goes down, then what do you think about the 3 kilogram mass? You bet. Is there any tension here? You. I mean you. Yeah, there's tension here. There's tension here. What do we know about Newton's third law? They're equal, aren't they? Every action has an equal and opposite reaction. These are connected. So if I'm asking you for tension right there, it would be the same as there, same as here, same as there, same as there, same on the top of the pulley, okay? It's the same everywhere. Tension is tension. They're connected. So if I ask you for the acceleration, tension at X. So let's remove some of these because it looks like I got things tied to my rope or chain or whatever you want to call it. Actually, I put in my picture I put it here, so let's just be consistent with my notes. So I want to find acceleration and tension. Well, if the 8 kilogram mass, we know it's going down, will it accelerate down? You bet, because that's how gravity works. The 3 kilogram mass will accelerate up. Is this acceleration equal to that acceleration just in the opposite direction? Yeah, assuming this thing doesn't stretch, and we're going to assume that. Okay, so tension's the same everywhere. Acceleration, if you know it on one mass, then it's going to be the same as the other guy, just in the other direction. Okay? So, free body diagrams. I just want to look at the 8 mass. Down, I have mg. Up, I have tension, right? And you can be specific and say it's not the 3 kilogram mass that's pulling on the 8 kilogram mass. It's just the rope right here that's pulling on it. Okay, there's tension there. And this guy, that's 3 kilograms. Down we have mg. Well, let's go 3g. And that's also tension. So let's change that mass so we can actually put 8, right? So in some textbooks, if you look in, and I think I was even taught this way, if I can remember that far back, but you can get two series of equations here, and then I will have two unknowns. I'm going to have acceleration, because I'm assuming this guy goes down, and I'm going to have this mass times acceleration, okay, which is 8. And then I can get another equation for this guy. Well, actually, it's going the opposite direction, isn't it? So my Newton's second law says the unbalanced force, the difference between these two, equals ma. And this guy also equals ma. And then I can substitute 1 for t and put it in the other equation and solve it for a. And that'll work. But I'm not going to do that. Okay, I prefer the kind of common sense method. We know which way this thing's going to go. Okay? If this 3 kilogram mass wasn't even there, this thing would fall at 9.8 meters a second, right? Okay. If this thing was 8 kilograms, we know this thing wouldn't move at all. Common sense. I know it's moving. The unbalanced force here is the difference of the two weights. Does that make sense? Okay. So what's causing this thing to move? Let's write down what I just said. The difference between weight is what causes movement, or in this case, well, it's going to accelerate, right? Acceleration, an unbalanced force. Again, this is the formula, but we need to understand the concept. We need to apply that formula. So what is the difference between the weights? 8 mg minus mg is the difference in the weights. That's going to cause the acceleration. That's going to be ma. So I know 8 minus 3, well, that's 5, right? So 5 times 9.8 is going to be the unbalanced force, the net force. That's going to cause the acceleration. The one thing we got to look out for here, though, is that's the mass of the entire system, okay? So all the masses. In this case, there's only 2. Okay? So that's this is my formula, that's my concept. So how do I solve that thing? For a, divide both sides by 8 plus 3. And my acceleration is, I don't have to worry about any degrees today, so I should be hunky-dory. 5 times 9.8 divided by 11 is 4.45 meters a second squared. Okay, so that's the first part. That's the acceleration of the system. We know what way. That one goes down, that one goes up, and if I'm talking signs, if I took that as positive, right? If I guessed wrong and got a negative, well, you know. But it's pretty simple to see which way this thing's going to go, unlike yesterday's problem, right? All right, that's A. How do I find the tension in the rope? I need to analyze one of these guys. Either that one or that one. It doesn't matter which one. Okay, maybe this one, because it's going in that direction, is easier to do. So let's look at this again. That's 8 kilograms. That's 8 times 9.8 that way. That's the tension up. Okay, which way does this go? Yeah, I know it goes that way, which means this is bigger than that. There's an unbalanced force here. So 8 times 9.8 minus tension, that's the unbalanced force, that's ma. Here, I'm just analyzing this one mass though, so don't put the masses of the entire system, just put that one. 8 times 9.8 minus t equals 8, and now I know the acceleration. That's 4.45. Only one unknown in there, that's t. Put it over there on that side, make it positive. Put that one over there and subtract it. Okay, that's the tension. Let's be fancy. I'll factor it. .8 newtons. Okay? And, like I said, that was this tension, but it's the same everywhere. So I don't care where you got X, that's the tension. Okay? Should I prove that it's going to be the same on the other one? Okay. Let's look at the other mass. That one's 3. I know down it's 3 times 9.8. Up its tension. Which way is this guy going though? He's going that way, which means this is bigger than that. Equals 3, 4.45. If I solve that for tension, then I get 3 times that plus 3 times that. And is that the same thing? You bet. Better be. Because tension's the same everywhere. Thank you, sir. All right. So that's an Atwood system, or call it pulleys. One more. Oh, let's go 10. Let's go 5. Example 2. Yeah, let's use English. How am I doing that? I don't know why I'm writing at an angle, I just started doing it. This is one of these maybe borderline common sense questions, but sometimes common sense takes a back seat. Here. Tension at X, okay, oh there's X, is 15. What's the tension at Y? And I was actually thinking about setting this up with some meters, and I still could do that. Maybe I'll do that tomorrow. I wish I had a prep this semester. Because again, it's when I tell you the answer, some of you are going to go, what? No, he's wrong. There's no way.
What's the answer?
I ain't telling you yet. Who likes A? Come on. Come on. Come on in. Jeff. Who likes B? Oh, see, it's people written that, and then they're looking at peripheral vision. They're like, whoa, I don't see any of their hands. No. C? You want to do, okay, there's 2 for A. C? You like C. D? And that's not as many hands as there are kids in the class. So the rest of you are this guy. Okay. We do know tension here is 15 newtons. What's tension here? So if I pull here with 15 and here with 15, that's 30. Does that seem weird?
Not really.
I think it seems weird. Intuitively, I would never have guessed that until someone told me or showed me, or I looked it in a book somewhere and went, what? Okay, but that's what it is.